Welcome, ladies and gentlemen, to day 14 of Advent of Code 2023. Let's dive in. I really enjoyed this puzzle. I'm not going to say it was fun, but it was fun. So, we reach the place where all of the mirrors were pointing. A massive parabolic reflector dish attached to the side of another large mountain. So, essentially, we've moved on, and we now have this new puzzle input. So, the puzzle that we're dealing with now, we have, again, another grid of dots, hashes, but this time we've got some extra zeros, I think they are. So, the rounded rocks will... so, essentially what we need to do is we need to tilt a platform. So this is the platform that we have, and we need to tilt it to the north. The rounded rocks will roll in the direction that it's tilted, when the cube-shaped rocks will stay in place. So that's the hashes, and we have the circular rocks that will roll. You note the positions of all the empty spaces with a dot, and the rocks your puzzle input. For example, this. Start by tilting the lever so that they all slide north. So we can see that they start to bunch up here. So in this far left column, they all start to bunch up. In the second column, they again all bunch up down here. Now in the third column, they actually get stopped. These two here get stopped by this hash, this square rock. You notice that the support beams along the north side of the wall are damaged. So to ensure that the platform doesn't collapse, you should calculate the total load on the north support beams. The amount of load is caused by a single rounded rock is equal to the number of rows from the rock to the south edge of the platform, including the row the rock is on. Cube-shaped rocks don't count towards the load. So, the amount of load is caused by each rock in each row as follows. So, we have 10 rows from the south. We have 1, 2, 3, 4, 5. So, that would be 50 plus 2 lots of 9 plus 4 lots of 8, so on and so forth. Total load is the sum of the load caused by all of the rounded rocks. In this example, the total load is 136. So essentially what we need to do is shift all of the rocks north, then count how many are in each row, and multiply that count by the row index reversed. So as you can see, 1 is all the way down here. So we need to check how far it is from the south to add it up. So let's dive in. This was a good little problem. So for the first part of this, first and second part, I did very different approaches. So I'm going to show you the 2 different approaches to it. Though the second approach could be used near enough for the first one, but I did it iteratively and then kind of simplified it a lot more for the second part because it was needed. Right, let's dive in. So part 1. Firstly, we need a grid of everything. So let's just get a grid, and this will be a list of lines for line in string dot split lines. Cool. So that's just going to give us a list of lists rather than a list of strings, because we want to modify bits and pieces as we go. So that's how we're going to do the first one, is actually modify all of the rows and columns, etc. Okay, so let's add a variable for new positions, and this is going to be a set. So my intention here is basically to start with, say for example, this row, this boulder, and see where it could move to, and then make a note of that new position that it is now in. And that way I can, for example, with this one here, I can shift it to here, and then if there was something after it, I can say there is also this new position, that's the one I'm caring about. And then each time I'm going to shift, I'm essentially going to start from the furthest away, and then go to no, I'm not going to start from the furthest away, sorry, because then that will potentially skip broken part, not broken, the square boulders. So we'll keep going upwards, but only look for the new position of something or a square. That's the only ones that we're gonna care about. Okay, so let's carry on. So we have these new positions. So for our row in enumerate grid, for C cell in enumerate the row, what we're then going to do is say if the cell is in, so let's go with a hash or a dot, because these are the only two things that these are the two that we can't move, so we're not going to try. So we'll just skip over those. So let's just say continue. We could also just say if it's not in, do this stuff, but if we were to, just a quick side note here, so if we would say not in here, then the code that we write here is an extra level of indentation, whereas if we instead have this as the kind of exit or the continue piece, then when we actually come to write the code for what we actually want to do, we're one level of indentation less, which is just a little bit easier to read. I always like to exit early as possible. I say always. There are going to be times when you see, and as you have seen in previous videos in this series, that there's nested if upon nested if, but yeah, for the most part, I do try to exit early and then, do the code that one extra level of indentation out as much as possible. So anyways, what we want to do now is we're going to start checking the rows. So let's say RR, so for the new set of rows, and let's set that initially to -1. So if we now just start a loop and continue, start a loop and just try to find the new position that we're going to move to, and then add the new position into there, into the set of new positions. So let's do while true, if this is less than 0, firstly, or the grid was almost good. Grid column is equal to a hash, or, so this accounts for we're moving upwards and we've gone off the grid, or we've hit a boulder. Now finally we're going to do a check to see if we have moved a round boulder to a new position already. So new positions. Then what we're going to do is we're going to say new positions dot add, and we are going to add RR plus 1 with the column. And the reason we're going to do +1 is because we've already gone down 1 to check to see if it's in that new position. What we could do instead is just say RR is equal to R, and then check the next one, and then we're just saying the new position is equal to R and C each time, rather than RR and C, rather than doing RR plus 1. But yeah, I just figure going down 1, we initially want to check the row below, so let's just start with that. So if it is in there, there's a new position, and now we're done. So let's just get rid of that one, or sorry, not get rid of, but break out of that. And then otherwise, so if we haven't been able to break out, so then we're just going to do RR minus equals 1. So then we're just gonna reduce it down, keep going up north until we get to the end. Okay, so now what we want to do, if we just go up here for a second, and from collections, import counter, collections, yeah, counter. Cool. So then what we want to do, once we have gone over everything, we're then going to say counter is equal to a counter, and we are going to get the rows from the rows from all the stuff that's in the new positions. So we're just going to say x0 for x in new positions, and then we're going to do total is equal to the sum of we want, what do we want? We want the length of the grid minus the key times the value for the key value in counter dot items. But we are going to need to wrap this, so we want to do this particular calculation first. We want to do grid minus k times v for kv in counter items. So all this is going to do, so we have the count of how many times the row has been put in, because we've got this new positions set. So if I actually just print, I'll show you what this will look like. print new positions, and then let's also print the counter, and then you can see what we're going to sum up there. So that should give us the output. So if we just go over here, run PyTest part 1 and part 2, so you can see all these different positions. The counter is then the row, and then the count of how many times it's been seen. So if we don't run part 2, don't run my actual input, but instead just run PyTest part 1, we don't get all of this output. Fair enough. Right, so we have all of this anyway. So this is the the row, the amount of items that are on the row, and then we have the actual amount that we're looking for. So if I go down here, 113486, 113486. So essentially, yeah, we've got all of these different coordinates, rows and columns. We're getting the row, which is the first entry from every single one, and then we're counting up the amount of times that's been seen. Yeah, essentially that's it for part 1. Now, so part 2, let's move on to part 2. So this one gets gets a lot trickier. So with part 2, it was kind of obvious from just move things north, and the fact that the button moves things in a direction. It was kind of obvious that we were going to go, here's a cycle. So the dish deforms, but not in a way that focuses the beam. To do that, you need to move the rocks to the edges of the platform. Fortunately, a button on the side of the panel controls labeled spin cycle. Each cycle tilts the platform 4 times so that the rounded rocks roll north, then west, then south, then east. So up, left, down, right. After each tilt, the rounded rocks roll as far as they can before the platform tilts in the next direction. So we go north and move everything up. We then go west and we move everything to the left. We go south and we move everything down. And we go east and we move everything to the right. After one cycle, the platform will have finished rolling the rounded rocks in those 4 directions in that order. Here's what happens in the example above after each of the first few cycles. So we have the first example after one cycle. So this has gone up, left, down, and right. After 2 cycles, after 3 cycles. So we have this shifting around, this counterclockwise movement for everything. But just to make things even harder, because initially I just thought, that's fine. Well, I'll just go up. I'll repeat the same thing going left, repeat the same thing going down, repeat the same thing going right. Nice and easy. But do it this many times, and I think this is, what's that? So we've got 3 zeros, 3, we've got a billion cycles, something like that. Yeah, to make sure that they'll survive for a while, you need to calculate the total load in the north support after 1 billion cycles. In the example above, after 1 billion cycles, the total load on the north wall is 64. Run the spin cycle for 1 billion cycles. Afterwards, what is the total load in the north beams? So what I initially did was I wanted to see how long just doing that would take. So I simply did a for x in this number, continue. Do nothing, continue for this amount of time, or for this amount of cycles. And I was waiting quite a while, and nothing happened. Clearly, there was no printing, there was no logic, there was nothing. So this is not a easy thing to just brute force. You could, but you'd just be waiting a long time, right? So instead, we need to be a bit more clever about it. Now, from earlier problems, earlier problem, first thing I thought here is we're doing a billion. There's clearly a cycle. We're clearly seeing the same thing multiple times as it goes round, right? So that is what we're going to try and find. Is find the cycle, and from there calculate, given a cycle, and how long that cycle is, where the cycle starts, where the cycle ends. Given that, we then can find out if we were to run this a billion times, which one would we end up on? Not necessarily running it a billion times, but actually just calculating based on the cycle. So let's dive in to this one. This was a good problem. So we have the grid again, but this time instead of doing a list, because we want to essentially cache this, we need to use a tuple, because we can't use a list as a key in a set. We can only use a tuple. So that's what we're going to do. I'm going to have a tuple or a tuple of string dot split lines. Okay, and that's all we get. We're not going to split it again from there. We'll do that, whatever stuff we need to do, but we're just going to make a tuple of strings. That's all we're going to do. Cool. Okay, so we have the grid. So now let's make that scene variable that I said, and let's then keep a track of the indexes of what we have seen. So let's do scene index, and this one we can have a grid, because we're going to use this as an index for getting the correct one out of scene. If that makes sense. Cool. And then let's just keep track of the count so that we know where we start to see a loop. Cool. So while true, what we want to do is reset the grid, move everything around by resetting the grid, or changing the grid. So let's firstly do that. So let's say update the grid. So this one here, we're going to say the grid we're going to do for underscore in range 4. So we're going to update the grid. But the way we're going to do it is by zipping over all of the rows, which is then going to give us essentially a slightly transformed grid in a so it's going to be a kind of a slight rotation not a rotation, sorry, like a flip and a rotate, almost like a diagonal flip. Is what we're gonna essentially get. So let's do grid is equal to a tuple, and we want to do a map with this dot join, and we're going to zip over the expanded grid that is there. So this will do kind of a diagonal flip in a direction, and then what we want to do there is now actually move all of the different points around. So if we do this, if we do tuple, so we're just going to modify it again, but this time we are going to do the sorting. So we've got the hash is what we want to join on, and we are going to join it all together by getting another join, but this one is going to be a sorted list of the basically the row grid, if you like, the row of the grid. And we're going to reverse that. Reverse equals true. And then from there, we just say for g in row dot split, and we're going to split that on hashes, and that is going to be for row in grid. Okay, so essentially we have flipped it on a diagonal, then we are splitting it apart by the hashes, so by all of these. So we're going to have I can't really demonstrate with just this because we haven't flipped it on a diagonal, but essentially it's going to be a diagonal flip. We're going to split on the hashes. We're then going to join it all together by sorting the dots and the circles that are left, which is going to push all of the circles to the end, but then we need to reverse that because we need them at the beginning. We then join that on the hashes. So as soon as we get to another hash, we're then going to have all the circles butted up against it. But it's still not quite right, because it's not been it's flipped on a diagonal. It's not been rotated. So then what we need to do is say grid is equal to a tuple of row, and then all we're going to do is reverse it for row in grid. And we're just going to do that 4 times. So then that will give us the new grid. There is our cycle. Cool. Code is unreachable. Okay. Right, so anyway, we get to there. That's been done multiple times. The cycle has been complete. Once the cycle has been complete, we then say count plus equals 1. If the grid is in scene, we are going to break. If it's not in the scene, then we're going to do scene.add the grid. And we're also going to do scene index dot append the grid. Okay, so that's going to give us, because we can get the index out of that, we're going to use that to later on get the correct grid from the scene. Cool. So then we'll break out of this as soon as there's a loop. So then what we want to do is we want to find the first entry. So let's say first is equal to the scene index dot index of the grid. So this has already done our loop. We've carried on while true until we get to the first point in time when the grid has already been done. It's already been seen in there. So as soon as it's been seen, we break out of this, and now we're down to our actual finding the cycle. So now, speaking of finding the cycle, so we're going to have the cycle is equal to the count minus the first. So the count we've been incrementing here, how many times it's taken us to get to this point, and then we're going to take away the first entry, first index of that same grid. Cool. So then to find the correct index, we then do the index is equal to, so it was 1 0 0 0 0 0 0 0 0 0. I think that was right. Do you know what? Let's just copy that in just to be safe. There we go. Yeah, I was right. So we've got the 1 billion minus the first, and we're then going to get the remainder of that against the cycle plus the first. So we've got the amount of the cycle, so we're going to get, if we were to take away from 1 billion the first index that we get to, we then see how long it get the remainder of dividing that by the cycle, or the remainder of the cycle into this. I can't remember the correct math terminology and all that kind of stuff, but we're getting the remainder, and then we're adding the first again, because we've taken it away here, we're going to add it back in. Cool. So then the entry that we want is equal to the scene index cool. So then we have counts is equal to, so let's say R for the index and the row in enumerate the entry. So what we want from this is the count and we want to see how many zeros, or is it O? I think it's O. How many O's there are multiplied by the length of the entry minus I for the index here. So what we're essentially doing is saying we start at 0. So for the 0th row, let's say this one, so at the 0th row, we want to get the length of all of this. So we're saying how many rows are there. We then take off 0 because we want it to be, that is, if you like, the rank of the row. So essentially the row order has been reversed, but only by index. So yeah, we do that. Counts as equal to that. And so then finally what we need to do is say the total is equal to the sum of the counts. Let's just see if that works for us. Yes, there we go. So part 1 and part 2, we get passing test, and we also get the 104409, which is exactly what we got here. And like I say, the reason for that is, the reason that ran quite quickly is because we're finding a cycle, and so we're only doing a very small amount here. So in fact, we can see how many we're actually doing. So if we print, if we get the first, we get the cycle. If we get the count, that'll be interesting. And I say interesting. None of this is probably very interesting for anyone watching, but whatever. So we have all of these. So if we just see what we're getting here, and we print this, so we can see that the first time that we see the one that is repeated is the 81st index. The cycle lasts for 38. So when we get to a cycle, it's 38 rounds to get to a cycle. And count of 119, so that's essentially that added together. So yeah, there we go. Yeah, the count, the cycle is the count minus the first. Yeah, so the count minus the first is equal to the cycle. So therefore, those two added together is the count. Yeah, there we go. So this gives us the actual index that we actually want. Because we have to jump through, we're getting the remainder so that we can add on the first time that we see it as well. So yeah, there we go. That was a really cool problem. Relatively good timing, 37 minutes to explain it. Hopefully I've explained it well enough. If I haven't, let me know in the comments down below, obviously. Yeah, if you're liking these videos, like and subscribe if you want to see more. If you want to tell me how terrible they are, comment. If you want to tell me that they are bearable and that you enjoy listening to my monotone British voice, tell me in the comments down below. Yeah, there we go. Right, see you for day 15. Day 15. Have a good one.